morning.
Are there any questions? Okay, let's just see where we've come this semester so far. We have this class and one more class on Monday before the final. We started out the semester with some general notions of control, of where we want to go, what the whole point of control is, what our goals are. And then what we said is, in order to actually do control, first you have to know how to do modeling, because your control is based on model. So we spoke about doing models and about how to analyze models. And we saw that the models that we can analyze most simply are linear models, because we don't know how to solve nonlinear models in general, but we do know how to solve linear equations in general. So we introduced, even when models were nonlinear, we introduced a way of approximating them by linear models by doing the linearization. And we started out in that beginning of the semester by doing that and then solving the linear models using methods of ordinary differential equations. And that worked fine. The only thing was that had lots of algebra, so lots of easy ways to make mistakes, particularly under test time pressure. So we introduced another method, the method of, and by the way, what was new about those models from what you had in previous classes was the models in this class were time dependent. In all your other classes, formally, people write down on the first day of the semester the DDTs, and within a nanosecond they throw out the DDT and assume everything is steady state. In this class, the DDT is there whether we like it or not, and it's actually our friend, the DDT. Okay, so, and it's the whole basis of control. If there were no DDT, we wouldn't need control. So then we spoke about how to use Laplace transforms to drastically simplify the algebra. But there was some background in basic issues of complex variables that you needed to know in order to use and to understand Laplace transform. Of course, that was new math for most of you guys, but you're engineers, you can handle it. And then once we were happy that we knew how to do modeling, linearization, and solving linear models, we said, okay, we're half the semester's gone, now we can start doing control. So we started out by having a few canonical examples that we would do our control on. And we spoke about, by the way, when we were doing solutions to the linear equations, we spoke about issues of stability, how we determine stability from the solutions of the models. And then we also saw how, even without solving them from the Laplace transforms themselves, from the solution in Laplace space, we can usually answer most of the questions of interest of stability without even doing the inversion. So once we started doing control, we wrote a few canonical examples that we would test out all our control methods on. And we noted that the most popular controller, and the one that we would concentrate on in this class, was the so-called PID controller, proportional integral differential controller. It had three components, and it had lots of advantages, which we spoke about. But then it also had three parameters. It had a KC for the proportional controller, it had a TI for the integral controller, and it had a TD for the differential controller. And we saw that if you make KC big, the controller gets aggressive. And if you make TI small or TD small, you make the controller more aggressive. So what you want is, so we wanted to balance, if you make TD large, it's more aggressive. And if you make TI small, it's more aggressive. This TI comes in the denominator. So what we saw is that, gee, how do we choose these parameters? And that's called the tuning problem. So we noted that we introduced two methods, a brute force method, as well as a method of correlations, where if we could take our system, our plant or whatever, the control-free plant, and approximate it by a time delay in a first-order process in series, then we could non-dimensionalize the parameters and basically come up with correlations for good values of control. And that was moderately satisfying. It gave us reasonable values of the tuning parameters for the PID controller. Not necessarily optimal, but pretty good. But we didn't really talk about stability. We just said, in any quantitative way, we just said, if you make KC too big, it's going to go unstable. If you make TI too small, it's going to go unstable. If you make TD too big, it's going to go unstable. So what we did is we shifted gears and we said, okay, let's talk about stability. We want to understand this. Let's talk about stability. So we said, okay, how do we analyze stability? We analyze stability by, which we knew from the complex variables discussion earlier, Laplace transforms, we analyze stability by looking at the roots of the denominator of the final G, the overall G. So in this case, for example, if we had only a change in the set point, it would be CV prime over SP prime. And we'd be looking at this denominator. And that denominator is going to be some sort of polynomial, in this class, generally a polynomial in S. And if we look at the roots of that denominator, we know from the discussion of Laplace transforms that the zeros of that denominator are going to go into the exponents of the e to the x's, e to the t's, e to the something t's when I do the inversion. So obviously, if there's a positive real part, then that tells me that CV prime, when I invert it, is going to grow exponentially. That's bad. If all the roots of the denominator have negative real parts, we say, yes, that means everything's going to eventually go to the steady state. And if the roots are complex with negative real parts, it may oscillate to get there, but it'll get there. And if the roots are complex with a positive real part, when it's blowing up, it will oscillate. Very nice. So, and we saw that you can do that when I only have sort of one parameter to worry about. I can scan parameter space. So we did that in a case where we had proportional only control, where the only parameter I had to worry about was KC. Everything else was fixed. So then I could look at the zeros of this denominator for many different values of KC and see which ones are good, meaning which ones are going to give me only roots with negative real parts, and which ones are bad. And we call that the root locus, because locus is sort of finding the positions of the roots. However, once I start having not just a proportional controller, but a proportional integral, a proportional derivative, or PID, then I've got 3 parameters. And it'd be very hard, very, very laborious and very hard to explore 3-dimensional parameter space to look at the zeros of the denominator. So it's doable, more or less, but it may take from now until doomsday. So I'm sorry if I'm telling you stuff we've done before, but I think when we do something new, it's good to put it in the context of what we've done already. So you know, so it's not just a bunch of random issues that we're talking about. You know, there's a logic to the course. It all sort of fits together. So another method we said was the Baudet method. What was the Baudet method? The Baudet method said, well, start with the open loop system. And that way, if I have a change in the set point to something that's oscillating with a sine function, when it goes through the system, it gets modified by a GC, a GV, GP, and a GS. Because these are all linear models, that means that the frequency of the oscillation is going to be the same, but the amplitude could be different by an amplitude ratio, and there could be a phase lag. And what we said is, okay, great. So what comes out, CVM prime, is also a sine function with a phase lag and an amplitude ratio from what I started with. So why don't we, once we have that set up, steady state, we can close the loop. But before we close it, let's tune it by changing omega, by changing the frequency of the sine function, so that when CVM comes around the loop, it's exactly 180 degrees out of phase with what I started with. And if I do that, then when if I close the loop and just turn SP prime into a constant, then I'm going to have the sine function coming in that's upside down, With the minus sign, it'll get flipped, so it'll be just like the original sine function. When I subtract a constant, I will still get a sine function minus a constant. It's still a sine function. And now, that means that's going to be the error. When it goes around the loop again, it's going to be flipped 180 degrees, multiplied by the amplitude ratio, and then flip back and added to the original, to that sine function, to that original error. So what happens is if I have two sine functions in phase with each other, because that's what happens when I flip the minus after 180 degrees out of phase, then these two will add. And every time through the loop, it'll add again and again and again. So clearly, if this has magnitude, if we set this magnitude equal to 1, and this magnitude is greater than 1 or greater, then I'm going to be adding 1 plus something bigger than 1 plus something bigger than 1, etc., and that's going to blow up, and that's going to be unstable. On the other hand, if the amplitude ratio of this relative to this, that is the amplitude ratio of the open loop, is less than 1, then I'm going to be adding something to this that's smaller. And the next time through, it's going to be smaller by factor of the amplitude ratio squared. And the next time through, it's going to be smaller by factor of amplitude ratio cubed. And we know, I erased it, that 1 plus epsilon squared plus epsilon cubed is equal to 1 over 1 minus epsilon. So as long as epsilon is less than 1, it's a finite sum. It's finite. And if it's finite, that means the system's stable. It means a perturbation to this system will not grow to infinity. That's analogous to that really is connected to that notion of the exponents. If I were writing CV prime, remember, when it's a linear model, the inverse of the Laplace transform is going to be a whole sum of exponents, of exponentials in time, possibly multiplied by time to a power. The exponential is more important. And the important thing is the real part of the exponent positive or negative? Positive, bad. It blows up to infinity. Well, that would be if this had magnitude 1 or greater, the amplitude ratio. Then when I keep adding an infinite number of them, I'm going to blow up to infinity. On the other hand, exponent real part negative, that means it goes to a steady state. Well, if this is magnitude less than 1, then when I add an infinite number of them, 1 plus epsilon squared, I go to a finite value, steady state. So there's the connection. Okay, so, using this method, we spoke last time, we spent the whole class last time doing examples of how to use this method. And there were some two really important equations I needed. Because if I have a problem where I have a non-trivial GP, GV, GC, and GS, do I really want to calculate this whole ratio and then do the Baudet plots for it? It's a lot easier, since these are linear systems, it's a lot easier to use this fact that if I know the Baudet plots, the AR and the phi, for each individual piece, instead of recalculating it for this particular fraction, I know, and actually really all I need it for is for this particular set of four G's. Instead of recalculating it for this G open loop, what I can do is simply, if I know the original ones, I just take the overall amplitude ratio and I multiply them together. If I know the individual phase lags, I just add them. I think you left your notebook in my office, so you should take it. You should also come on time, but that's a different issue. At this point in the semester, I can't make people come on time anymore. Okay, so, and we looked at that in some great detail. So what I just sort of gathered on the blackboard before erasing were the pictures we drew last time. So here we had the Baudet plots for the first order system. The critical issue here was that phi went from 0 to minus pi over 2. So no matter what I do to omega, I can never get, in a first order system, I can never get 180 degrees out of phase. The second order system, it went from 0 to minus pi. So also, I never get there. I need to go to infinity to get there. So I never quite get to minus pi. So these systems are, if I just have a pure first or second order system, those are stable, according to the Baudet issue. But once I get a third order system, then the shape of the curve doesn't change, but now it can go down to minus 3 pi over 2, so it passes through minus pi. So once I get the third order, I can certainly get things unstable. We also looked at a delay, and we said a delay, well, that one is really bad, because the delay looks like an upside, the log phi versus log omega looks like an upside down exponential growth. Meaning this has no trouble getting to minus pi because it goes down to minus infinity. So what it says is, once I add a delay to any system, first order any system, then it makes it easy to get to minus pi. Of course, it depends on what the amplitude ratio is, whether it's going to be stable or unstable, what the amplitude ratio at the critical omega is, but I can certainly get there once I have a delay. Finally, I copied out of the textbook, I think I derived one of them, but in table 10.13, you've got Baudet plots for a lot of very typical systems, first order, second order, PI, PD, PID controller, etc. For the PI controller, the phi goes from minus pi over 2 to 0, but it goes in the opposite way of the first order system. In the first order system, it goes down as omega goes up. Here it goes up as omega goes up. And the PD controller is kind of a cool one, because this one, instead of staying negative, it goes from 0 to plus pi over 2. And we'll talk about that a little later. And at the end of the hour, I started to look at the integrator system. So why don't we look at the integrator system and continue with that? Are there any questions about my sort of context summary of the semester so far? Okay, so if you remember, here's the algebra. I didn't bother rewriting it or erasing it. It was too much to rewrite, so it's still on the blackboard. So here's the integrator. We said for an integrator, GP is 1 over AS. And since it's 1 over AS, we can calculate the amplitude ratio, 1 over the magnitude of A times omega. But phi is a constant, because this just is purely imaginary. So it's minus pi over 2. So if I draw the Baudet plot for a pure integrator, phi is always minus pi over 2. But the amplitude ratio is just a straight, the log AR versus log omega is just a straight line of slope minus 1. Because if I take the log of this, I get minus the log of A minus log omega. So this is minus the log of A. That's log omega, just has slope minus 1. So clearly this thing is stable. The plane integrator, I shouldn't really say that. What I should say is the pure integrator, phi never gets less than minus pi over 2. Well, what happens, now of course, so what happens, so I don't want to make a conclusion about that being stable. What I would like to say is what happens when I put proportional control in. When I put proportional control in, we see that the system just rearranges to a first order system. When it becomes and we know what first order systems are like. First order systems have no problem, they stay stable, because I have phi never gets less than minus pi over 2, and the amplitude ratio, so since this never gets below minus pi over 2, never gets to minus pi, we're okay. Well, what happens if I, instead of putting PI control, let's say I take the integrator and I add PI control, not just P control. So this was proportional control, and let's say instead of that I do proportional integral control. So if I want proportional integral control, I've got the integrator here as this, and I've got PI control. So let's see what happens when I add these two. So notice when I have a PI controller, I didn't even have to write it. So here phi is always minus pi over 2. We know that phi of the sum of these two, when I use an integrator and PI control, so this is GP and this is GC, then phi overall of the open loop is just the sum of these. So if I add them, then you see this goes down to minus pi over 2, and now I subtract the minus pi over 2. So the sum goes from minus pi over 2 to minus pi. So that tells me I almost get to 180 degrees out of phase, but I never quite get there. So log phi versus log omega goes from minus pi over 2 to minus pi now. And when you almost get there, like in the second order system, but you never quite get there, I call this marginally stable. Because I'm still stable, but I'm getting real close to possibly being unstable. Okay, so how about another system that might be marginally stable? Let's look at the pure delay. If I look at the pure delay, notice that the pure delay has no problem getting to minus pi. However, once I get to minus pi, I still have to go up to and find the amplitude ratio at omega critical. So if this is, say, minus pi, then this becomes omega critical. And when I look at omega critical, and I go up here, I get the amplitude ratio is 1. So if the amplitude ratio is 1, that again says it's marginally stable. It's not growing, it's not shrinking. It's just barely. It's marginally unstable. Why is it marginally unstable? Because if I add 1 plus 1 plus 1 plus 1 plus 1, I get to infinity. But I don't get there really quickly. If I added 1 plus 2 plus 4 plus 8, I would get there a lot faster. And if I had a tiny bit less than 1 plus 0.99 plus 0.99 squared, etc., that would add up to something finite. So that's sort of the notion of marginally unstable or marginally stable. I can also note that if I only have proportional control, that is, I only have one parameter, then the whole notion of stability is kind of easy to deal with because the amplitude ratio is just proportional to Kc. So if I want to make the amplitude rate, if I know, say, omega critical, so let's say if I have proportional only control. So in that case, Gc, for proportional only control, Gc is just a constant, it's just Kc. So let's calculate the amplitude ratio and the and phi. So the amplitude ratio, AR, for proportional only control, is just the magnitude of Gc of I omega. Well, Gc is just a constant, so it's just Kc. And phi is just the arctangent of the imaginary part of Gc of I omega over the real part of Gc of I omega. But Gc of I omega is just Kc, which is purely real. So the imaginary part is 0, so it's the arctangent of 0, which is just 0. So for proportional only control, things are really easy. Let's put proportional only control here. Log AR versus log omega. It's just a constant. Just Kc. And for the log phi versus log omega, well, it's just always 0. So what does that tell me? That says that issues of stability are really easy here because by changing Kc, I don't change phi. So I don't change omega critical when I'm putting it together with everything else because it adds nothing to the total phi. I can change Kc, it doesn't change anything for that. And it just multiplies the amplitude ratio by a constant. So that tells me if I have a problem that is proportional only control, and I find that it's unstable because the overall phi goes to minus pi, I can find an omega critical I go up to find the amplitude ratio to make it critical. If it's too high, then I just make KC smaller and I'll bring that amplitude ratio down. If it's really tiny and I want a more aggressive controller, I can push it up by increasing KC without making the system unstable. So that's sort of a particularly easy case. It gets more interesting when I get to when you use PI, PD, or PID control. Any questions on that? Doing a lot of talking and I haven't written many equations. That's how unlike me. Okay, so questions? Okay, so as I mentioned in the overall intro about 15 minutes ago, when we had the PID, introduced the PID controller, we noted that there were 3 parameters and that we had to tune with KC, TI, TD. We want to tune them so that if there's a disturbance or change in the set point, we go fairly quickly back to the set point we want, but not so quickly that the system blows up and it becomes unstable. So obviously if it takes forever to get there, it's not going to be unstable, but it's not desirable. If you make the controller too aggressive, then you think you're going to get there, but you overshoot, and then the system blows up. So you want to find that compromise, and the methods we spoke about were sort of brute force as well as correlations relative to a particular model, where the particular model was a pure delay followed by a first order process. If your true system, if your true GP can be approximated well by a time pure delay followed by a first order process, do it, use those correlations. But if that is a pretty crappy approximation, then that's not a good way to go, ends on your system. And what we would like, if you remember when we did those correlations, stability was an afterthought. We said, okay, use these numbers, and if you're too aggressive, lower them because the system's unstable. But the correlations themselves didn't have stability built in. So now that we know something about another method, this Baudet method for stability, we can try to develop correlations that take stability into account. So stability-based correlation. For the PID controller. And these were first done in the 1940s, so that's a long time ago, 80 years ago, by Ziegler and Nicholson. And these are called the Ziegler, I don't know, if he was American it would be Ziegler, if he was German it would be Ziegler. Ziegler-Nicholson correlations. So let's discuss the Ziegler-Nicholson correlations. Okay, so what do? So in the Ziegler-Nicholson correlations, you do the Baudet plot for your system. Assuming KC is 1. So do the plots for your system with P only control. For KC is equal to 1. So take proportional only control, the easy one, set KC equal to 1, and do the Baudet plots. From the Baudet plots, you're going to get, so this will give you an omega critical, and it will give you an amplitude ratio. Critical. And now I want to define two quantities. So is it clear how to do this? So then what you do is I'm going to define KU. U stands for ultimate, like ultimate frisbee. And I'm going to define that as 1 over AR critical. And I'm also going to define a period. What's the notation for that? PC. PC star. Don't ask me why they chose that notation. It's probably before they had, it was 1940s, they didn't have computer PCs, so it didn't ring that bell. And that's going to be defined as 2 pi over omega critical. Right definition? Yes. Okay, so now let's just check the units of this. Omega is a frequency, so it has units of inverse time. So this has units of time. This has units of amplitude ratio is dimensionless. So Ku, the ultimate K, ultimate frisbee, is dimensionless. Well, actually, that's not true. The amplitude ratio has units of output over input. So this has units of, AR has units of output over input. Meaning input is units of set point and output is units of CV. This is units of, well, so it should actually be dimensionless because they should be, this is measured so it's the same units as SP. So it should be dimensionless. If we've done things right, this should be dimensionless. Non-dimensional. Okay, and then once I have these quantities, and remember these quantities are based on the stability analysis, they're based on the Bode stability analysis. Then there is a bunch of there are these correlations. So now there's a new correlation which says, what do I do for Kc, Ti, and Td? If I'm using proportional only controller, proportional integral, or PID controller. And this, I'm just going to copy, memorize that. It says use K ultimate over 2, if it's proportional only. If it's PI, then use K ultimate over 2.2. And for TI, use, actually we call this PU, not PC stuff, PU. PU over 1.2. And if you're using a PID controller, it's KU over 1.7, PU over 2, and PU over 8. Let's look at this for a second. So we know that if I use KU and I have proportional only control, I will be marginally stable. I'll be marginally stable because if I use KU, then that tells me that the amplitude ratio will be exact, once I change Kc, will be exactly 1. And the amplitude ratio of exactly 1 is too dangerous. I'm marginally stable. Any little fly can kick me over the edge and the thing's going to blow up. So if I'm using a proportional only control for safety, it's still fairly aggressive, but I just use Ku over 2, which tells me that the amplitude ratio with that value of Kc will just be equal to 1/2, which is okay at omega critical. Notice if I go to proportional integral control, then I need to be less aggressive with K. So I divide by 2.2. 0.5 isn't good enough. I need to be a little bit lower. And we'll see why in a couple of minutes. Interestingly, and maybe we can see why now. Why is it that I need to be less aggressive with PI control, at least as far as Kc, than with P control? Well, notice when I have PI control, at low values of omega, this goes from 0 to minus pi over 2. So what happens is when I add PI control to the rest of my system, here's the rest of my system. If I had proportional only control, I was adding 0. So the phi was wherever it was. When I add PI control, I lower phi for small omegas. So that tells me it's easier to get to minus pi. Moreover, not only is it easier to get to minus pi, but if I'm lowering it over here, I'm more likely to get an omega critical that's smaller because I'm lowering the phi curve more at small omegas. So I'm likely to get an omega, it's making the omega critical smaller. Remember, if omega critical is smaller and the AR curves are monotonically decreasing, if I make my omega critical smaller, I make my amplitude ratio higher. So that tells me PI control is a little more destabilizing than P only control. And that's why I need to be more careful with PI control than with P control, because it's a little bit destabilizing. Now, that doesn't mean that I don't want to use PI control, because P control, proportionality control, gives me a long-term offset. PI control gets rid of the offset, but it's always a compromise. It's always like if you're looking for the perfect partner, you have your list of things, and then you meet someone, and they're never all of them, so you always say, all right, I'll take this one, and I'll compromise on that one. It's always a compromise. You never get the perfect mate, and you never get the perfect control here. I have to compromise. PI gets rid of the offset, but it makes things a little less stable, so I have to compromise and use a smaller value here. So we're sort of married to our controller in this scheme, of course. Next thing, what happens if I go to PID? What I didn't put in here is PD. What happens with PD? PD control, notice PD control is interesting. It goes from 0 to plus pi over 2. So what does that tell me? That tells me it raises phi. If it raises the overall phi, that's pushing the, first of all, it could raise it to a point that it never reaches minus pi. That looks like it makes it a little more stable. But even if it does reach minus pi, it makes it till I'll have to go further out to the right till I get to minus pi. So it's increasing omega critical. So in this sense, if the differential controller isn't too aggressive, it can actually make the system more stable. If it makes us more stable, I don't need to be as conservative with KC as I was with the PI controller. And you can imagine, I don't have the numbers for PD, but if I had a PD controller, I could probably use a number smaller than, so in fact, even here, I'm using a number smaller than 2. That is, this is a bigger value, not only than this, but even than this. You can imagine for a PD controller, I might want to use an even bigger value. However, that's KC. I also have TD, and I better make sure that's not too big, because even though this guy makes the system more stable, this guy can make the system more unstable. So that's sort of the logic behind these coefficients. And again, notice that when I put the differential controller in, I need to be more conservative on the integral. When I put the D in, let's just see. So here I need to be, here I shorten TI, so when I put the TD in, I could be a little, remember, when TI gets smaller, I'm more aggressive. When KC gets bigger, I'm more aggressive. When TD gets bigger, I'm more aggressive. The TI sits in the denominator. When it's smaller, it's more aggressive. So this tells me when I have the differential controller here, I can be a bit more aggressive on the integral controller, because I can make this smaller. So the exact numbers come from the correlation, but the directions that the numbers go make perfect sense. Any questions on that? Now, what we said here is we would do this analysis from our model. Sometimes if I don't have a model, let's say I have a complicated system, I don't have the model, or I don't believe the model, I can also do it experimentally. That is, I can come up with a KU and a PU, that is, coming up with a AR critical and omega critical. I can come up with them experimentally. How do I do that experimentally? Well, how would I do it experimentally? So clearly I know how to do it theoretically. Let's see how I would do it experimentally. If I would do it experimentally, meaning I have this complicated process, I don't have a good model. I just want to see if I can do this analysis experimentally. So, and I have some notes on that, so why don't I just look at them before I tell you how to do it, so I get it right. By the way, this is called closed-loop continuous control, or continuous cycling. Okay. So, experimentally. Of omega critical and AR. And this is called closed loop. Closed loop what? Closed loop continuous cycling, I believe. Closed loop, yeah, continuous cycling. So what you do is you do the experimental analog of this procedure. So do proportional only control and a small casing. And introduce a small SP prime. And then observe the dynamics. Okay, remember, I've got proportional only control, and KC is really small, so it's not aggressive. And the assumption is, with weak enough control, the system is not going to blow up. That is, for all these methods, I'm always assuming that this is stable. Assume that GLP loop is stable. So that's easy enough to test. I just try it out, see if it blows up. I can start out with KCB 0 or KCB very small. And I observe the dynamics. And let's see what happens. Well, if I observe the dynamics and things are stable, or they can be unstable. If the dynamics are unstable for the value of KC I chose, make KC smaller. If it's stable, make KC bigger. And you do this until the dynamics are sustained oscillations. That is, we know that, what's going on? We know that if the control is really good, you just get overdamped. It just goes exponentially where it's going. I know if I increase the controller a little too much, then it's not going to go exponentially. It'll go, but it'll be underdamped. So, if KC really small and system stable, then CV prime over T is just going to go exponentially. If KC is bigger, a little bigger, then CV prime versus T is going to oscillate, but it'll eventually get. It's going to be underdamped. If KC is just at the border, then I'm going to get sustained oscillations. And of course, if Kc is too big, then versus t, and here's where this is t is equal to 0 is where the perturbation comes in, where the change in set point, takes hold. Here I've done it for perturbation. Then, of course, this will oscillate and grow. And if it gets even bigger, it may just grow without oscillating. So what I want to do is, if I start out with a Kc too big, I want to go down until I find this. If I start out with a Kc too small, if I see either of these, I increase it till I get here. And what's happening when I get here? When I get here, that means that the exponents, when I do the inversion, the exponents are purely imaginary. Because if they had a real part that was non-zero, they'd either grow or decay. So if this is purely imaginary, that tells me the real part is 0. If the real part is 0, that's marginally stable. And that value of Kc that gets me that is just Ku. That just becomes Ku. And the frequency of this oscillation, remember the frequency of the output is the same as the frequency of the input. So the oscillatory frequency, this frequency, oscillatory frequency is just omega critical. So there I've experimentally determined K I've already, I'm sorry, this is Kc. Is Ku and Pu. So I've got omega critical and I've got Ku. And I have those, and then I go through when I use these correlations. So that's how we do it experimentally. Before I do an example, let's just make a comment about how these correlations compare with the correlations we had before. So how do the Segren-Nicholson correlations compare with the earlier correlations? Remember, the earlier correlations were not based on stability. They were just based on a plug flow followed by a CSTR, a delay in a CSTR. These are, because they depend on the Baudet analysis, these are stability based. So let me give you a little graph that's typical of this. So here is KC-Kp versus theta star. And if you remember, the KC-Kp curve looks something like this. This was the old correlations. Old correlation. And the Segren-Nicholson correlation looks something like this. So the Segren-Nicholson correlation, since it has stability built in, it allows you to get a little bit more aggressive, even at low values. Where here we had to be really careful, because this is a correlation, we didn't know what the hell was going on. Here the Segren-Nicholson said, I know what's going on. And I figured out stability so I could be a bit more aggressive. So that's the difference there. And I do want to note that, remember, stability only depends on the roots of the denominator. Even though we're doing it by another method, stability only depends on the roots of the denominator. But the actual dynamics, that is, how fast will you go? So the denominator determines stability. Will the system blow up? But what else goes into these correlations is not just stability, because what determines how fast you go to the answer, and whether you go there at all with an offset or how fast you get there, that doesn't only depend on the denominator, it also depends on d and d prime, if you have a disturbance. So we should note that whereas stability only depends on zeros of 1 plus GP, GV, GC, GS, the dynamics, meaning do you go to the set point and how fast? Also depend on GD and the prime tilde. Depends on everything. So if you're only interested in stability, you only worry about the denominator. But when we tune our controller, we want it to be stable, but we also wanted to get rid of the offset and to get there in a reasonable amount of time. So that's why the correlations are not simply, that's why we're not simply using KU. We want stability, but we also want it to get there in a reasonable amount of time. So there are two issues there. The other thing to note in all the correlations, both these and the earlier ones, is that theta, the delay, is really the most important thing going on. The delay is more important than even than the time constants of your system, usually. Because the delay makes these things drop down really quickly. Theta is really the most important. And as we saw here, that delays have a major impact on stability because they drop the total phi. When you add a delay to anything else, since this goes exponentially down to minus infinity, it lowers the total phi a lot. And if it lowers the total phi a lot, it moves omega critical to the left. And as long as the amplitude ratio occurs monotonically decreasing, as omega critical moves to the left, the amplitude ratio at omega critical goes up. And that's a bad thing, because then it's more likely that I can get past 1. So those are some general considerations, and now we could do an example or two. Are there any questions? Dynamics. Do you, okay, I failed penmanship. My worst subject was penmanship. Do you go to the set point and how fast? Sure. Any other questions? Any non-handwriting based questions? Okay, so let's just, go through sort of the mechanics of this. There may be one, no, I'll talk about that afterwards. Okay, so let's look at our canonical example. By the way, does everyone have the page with the canonical examples, which I photocopied? Yeah. But half the people often don't come to class, so you may not have this. Does everyone have this page?
I didn't bring it with me.
Well, if you need one, you can pick it up at the end of class if you don't have it now. So remember we had our canonical example where this was A, this was B, and then we had 3 CSP arguments. And here we analyze the concentration, and if we like it, we can do this because this was XAA, XAB, and here I had VA, VB, and we had XAA is much bigger than XAB, and VA is much less than VB. So that was our canonical example. We have it worked out here. And what I'd like to do is I'd like to look at how we actually do the tuning here. So let's take specific numbers. So in this case, let's let GP be equal to 0.039. Somehow we like that 0.039. It pops up in all these examples, over 1 plus 5s squared. And this is Q. So again, this thing is Kp, and this thing is T. And that's, I think, the same one I had here. But this was one CSTR, we're now doing 2 CSTRs. So Kp over 1 plus St squared. And so what happens there? Is there anything else I need as an input here? Yeah, so let's look at the amplitude ratio and phi. So the amplitude ratio, well, we know that the amplitude ratio for 3 CSTRs in series is the product of the amplitude ratios of each one of them. And each one of them looks like this. So, but the 0.039 is the Kp for the whole thing. So I'm just going to have the denominator cubed. So I'm going to get a 0.039 over 1 plus 25 omega squared to the 3 halves. And log phi, well, I just add up the phis of all 3 of these. So this is just for the 3 CSTRs. This is just the 3 CSTRs. Just for GP. Or actually, why not just say for the process, for phi p, not the controller. So phi p is the sum of the phis for each of the 3 CSTRs. And each CSTR has a phi that's minus, that's just the arctangent of minus 5 omega. If I sum up 3 of those, I get 3 times. Now remember, I've assumed that they're all the same size. If they weren't the same size, then t would be different for each one. I'd have a t1, a t2, t3, and I'd have a square root 1 plus t1s times the square root of 1 plus t2s times the square root of 1 plus t3s. But if t1, t2, and t3 are the same, I just get that thing to the 3 halves. No, this one's cubed. This is to the 3 halves. Similarly, if I had different t's, then this would be arctangent of minus omega t1 plus arctangent of minus omega t2 plus arctangent of minus omega t3. But since they're the same, it's just 3 times that. Okay, so, and we know what these things look like. They look like third order. They look like this. It's third order. Now, I want to put a controller on this. What kind of controller do I want to put on this? Okay, well, so also I'm going to, yeah. So I want to put a controller on this. What kind of controller are we putting here? Proportional only controller. So now let's do proportional only, P only controller. Oh yes, I need this because I'm using the Ziegler-Nicholson. So when I do it for Ziegler-Nicholson, I have to, Ziegler-Nicholson says I use a proportional only controller with Kc equal to 1. And now we're going to determine Ku and Pu. So that tells me that G total, so now I look at, now what does Kc add to AR and to phi p? Well, Kc, for the proportional only controller, just multiplies the amplitude ratio, but it adds nothing to phi. So now when I look at the third order system, I look at this, I find omega critical. And then I go over here at omega critical, and I read over to get AR critical. And I take 1 over AR critical to get Ku. And if I do that, I get Ku is equal to. Ku is equal to, for numbers, where did it go? 208. And Pu is equal to 2 pi over omega c, which is 17.9 minutes. Ku is dimensionless, because we said it should be dimensionless. And now, so remember, this is I'm going through, this is step one. Proportionality controller in case equals 1. I determined this. This was from step 1. Now I want to use, PI control. Well, once I've got a KU and a PU, and I want to use PI control, I set KC equal to KU over 2.2, and TI equal to PU over 1.2. Actually, why don't I do it down here? So PI control, I set KC equal to KU 208 over 2.2. And you can do that arithmetic yourself. And I said TI equal to PU, which is 17.9, divided by 1.2. Again, I'll allow you to do that arithmetic yourself. And what happens when I do that? When I do that, and you plug in, you actually set your controller, then you always have to do fine tuning. So what you find when you do that, so here is C3, comes out here, CA3 versus T. And what you find is if you have this change, is this change a set point or disturbance? I think this is just a disturbance. This is disturbance. What you find is it goes back to the set point, but it takes a while. So this is for disturbance. And if you look at the controller, the manipulated variable, valve, versus T. The valve was over here, and it's going to be out of phase with that. So what you find when you do this is it does a reasonable job. It's stable, but it takes too long. So this is, of course, always initial tuning. Then what you would do is you would fine-tune. When you fine-tune, you would try to slightly adjust, make the system a bit more aggressive, a little higher value of K. Well, the problem is it's not going to the, it's not going here fast enough. So you would make the integral controller a little more aggressive. You make the integral controller more aggressive by shortening the time, So my initial tuning and then my fine tuning would be to lower TI. Lower it a little bit at a time to make sure you don't make things unstable till it gets, till you have less oscillations to get to your set point. And again, you don't want these oscillations because to take too long, because the manipulated variable, the valve keeps going on and off, opening, closing, eventually it's going to break. So you don't want it to break. Are there any questions on that? Why don't we look at another example? Example 2. So in this case, I'm going to use a second order system with a delay. 2 CSDRs with a delay. And I'm going to need this part of black. Two CSDRs in series plus a delay. So let's see what happens in that case. If I've got 2 CSDRs in series, I've got a second order system. Here we go. 0 to minus pi. When I add a delay, here's my delay. So notice the second order system was marginally stable and never got to minus pi, so I never had to worry. When I add the delay, even a tiny delay, even a small delay, since this thing goes exponentially to minus infinity, I'm going to make this thing, particularly at some value of omega out here, I'm going to make it less than minus pi. So when I do that, when I add these two, what's going to happen? It's going to start looking like this, but then instead of flattening out, it's going to keep going down. And when I get to the minus pi, I'm going to get an omega critical. And I'm going to look over here to get an amplitude ratio. if the amplitude ratio is still less than 1, then I'm okay. The system is still stable. But notice, the larger I make the delay, so this is this is the delay of unit 1. If I have a delay omega theta, if the delay is theta minutes instead of 1 minute, then this is going to start going down faster. Because this is log omega theta, so it's going to go down faster. So that means it's going to make the overall phi faster for the second order system. And that means, since it goes down faster, that means it's going to reach minus pi at a lower omega. So omega critical is going to be smaller, and therefore it's going to hit, instead of hitting the amplitude ratio here, it's going to hit here. So again, that's telling us that the larger theta, the more unstable the system. And that's sort of the situation here in this example. I'm not going to bother putting numbers in. You can just look them up in the textbook. But yeah, so we write out GP, write out phi. That's no big deal. The important thing here is phi total is equal to minus omega plus phi of the 2 CSTRs. Phi of the 2 CSTRs, remember this thing is 2 arctangent of minus omega t. And this is going to be minus omega theta, where that's the delay. But, so let's say the system is stable. So let's go back now. Now, let's go through the Ziegler-Nicholson. So let's say I find omega critical, and the amplitude ratio at omega critical is less than 1. So things are stable. Lovely. Now what I do is I add proportional control. I do step 1. I add proportional control. How does that for Kc is equal to 1? If I add proportional control, I'm not affecting phi, and Kc is 1. Not affecting phi, so Kc is 1. So obviously that's what I've done already. If Kc was 1, that's exactly the calculation I've done already. So now I say Ku equal to 1 over the amplitude ratio at omega critical. And Pu is 2 pi over omega. So I have those, and again, I use this correlation to get the tuning constants. And that's my initial tuning. Of course, I would have to do some fine tuning after that. So, and there really wasn't much to write on this. You can actually look at the numbers, but I just went through exactly what we do there. Are there any questions on that? Okay. Right. Okay, I've been covering stuff. This whole lecture was all this stuff is in chapter 10, but in a different order. Because I found that this order, the way I'm doing it, is more logical to me than the way it is in the textbook. Okay, so what about model errors? So far we've spoken about, in this class today, we have models, we have tuning techniques, Ziegler-Nicholson. And obviously the Ziegler-Nicholson says my initial tuning is based on my faith in the model, my trust in the model. Obviously, if the model isn't perfect, is never perfect, then I need to do my fine tuning afterwards. I do my fine tuning. However, how does model error really enter into things? What is the issue? What are the issues with model error? Well, the Ziegler-Nicholson correlations, as well as all correlations, have a little bit of model error built in. They're assuming the model's not perfect. That's why they're fairly conservative. They're divided by 2 and not by 1.1, because they have some model error built in. And there are a few things I want to say about this, but I only have 5 minutes, so let's see what I would like, what's the most important to say today. Okay, there are a couple of things to say. First thing is, when I do my Baudet stability analysis, obviously the Baudet stability analysis depended on the model, because it's my model that gave me the G's, which then gave me the Baudet plots. I want you to notice something. Let's say I have a model that's good in some regions of omega and shitty in, I shouldn't use that word, and lousy in other regions. So let's say, for example, that the model is good here, around here, but, well, why don't I do it somewhere else? So, model error. So let's say I have a log of the amplitude ratio versus a log of omega. And then the model looks something like this. And let's assume that the model is real. So this is the model, the white. But the true system looks something more like this. The real system. Well, what sort of effect is that? Well, that all depends. But if I'm looking at log of phi versus a log omega, and if omega critical is here, then it doesn't matter that the model is sucky over here. It's good over here, and that's all I need. But if omega critical is here, then here it really matters, because I get a big difference in the amplitude ratio. So what that's telling me is the model only needs to be accurate around omega critical for this analysis. The only problem is I don't know a priori where omega critical is. Also, the model may change where omega critical is. The model error may change this curve as well. But if it doesn't change this curve much, then the model only needs to be accurate near omega critical. It doesn't need to be accurate elsewhere, because the only part that matters is omega critical for the stability analysis. Okay, so what else should we say about model error? So the first issue is model only needs to be near omega critical for Baudet stability. Now, of course, it still needs to be good for the dynamics, because the dynamics doesn't just depend on the stability, it depends on everything. So it's, for Baudet stability, it only has to be good near omega critical, but for dynamics, it has to be good everywhere. How does, as we said, Ziegler-Nicholson builds in possibility of model error. And how do I deal with that? I deal with that with two issues. I deal with it with what's called a gain margin. And what's the other thing called? Which we'll call a GM. A gain margin and a phase margin. PM. Now, what's the motivation for that? I don't know if I'll get to give you the formula today, but the gain margin says there might be an error in the amplitude ratio. So if I'm looking for a cutoff of 1, maybe 1 is not a good idea because I may come up with a cutoff of 1, but if I have a 10% model error, that might really be 1.1. So what I think is going to be marginally stable is really unstable. Similarly, there's a phase margin. I calculate from the phase omega critical. Well, is omega critical exactly 2.37527 per minute? Or is it approximately that? So when I actually do my calculations, how much slop should I leave? That is, when I calculate omega critical, I should really calculate omega critical plus or minus something. When I calculate an amplitude ratio at omega critical, it should be omega critical plus or, amplitude ratio to omega critical plus or minus a little slop. And from the, how much slop? The slop is generally, so phi will generally go to phi plus, well, phi is equal to minus pi. Instead of minus pi, we'll usually take phi, minus pi plus or minus this slop, Pn. So we'll look at a little range of omega criticals. And similarly, the amplitude ratio would, so what do we typically take as Pm? And as Pm, we typically take about pi over 6. A typical number. So when we're looking for minus pi, we usually go up and down by about pi over 6. When we're looking at the gain margin, so how much are we dealing with here? We typically define the gain margin. We typically use a gain margin that's 1 over the open loop, that is the amplitude ratio of I omega critical. In other words, 1 over the amplitude ratio at omega critical. So I take the amplitude ratio plus or minus 1 over the amplitude critical. So I thought I shut that off. So that's sort of how I deal with slop in the due to model errors. Are there any questions on any of that? Okay, so that pretty much covers most of what we're doing in Chapter 10. I'll mention a little bit more about the rest of Chapter 10 in the next class, and then I'll talk about some more modern issues in control rather than just going on to the next chapter. I'll try to give you some sense of where control has come since the 1970s. What you'll find is that there is, in the rest of the chapter, they talk about other ways of tuning the controllers. There are lots of ways. And they're talking about methods that were developed from 1940s to about 1975. 1975 was a long time ago. And there have been plenty of people who've been making a living doing control since 1975. You know, it's 45 years ago. So I'll try to give you a sense of where things have gone since then. And what you'll find, I'm not sure exactly, I haven't prepared that yet. But what you'll find is people apply control to all sorts of stuff these days. For example, one area of control that became hot 20 years ago is to use control theory to figure out how to dose chemotherapy for cancer patients. For example, do you give them 1 shot a week? That's a big shot, or a lot of little shots? What's the best way to do it? And that was a system that people recognized 20 years ago was ripe for using control theory. If you could find out enough about GP, then you could apply control theory to that. And there are many other applications of control theory. If you look at those segways, anyone ever ride a Segway? Do you know what a Segway is? Why don't you fall on your face when you're on a Segway? It's not because you have great balance. It's because you may, but when you lean a little bit forward to get it to go forward, there's a control system that has a restoring force to make sure you don't fall on your face. Similarly, when you, obviously, you can override it. So that's another application of the control system. Okay, we'll talk more about these things next time. Questions? Remember, there were homeworks due. It's a really good idea to do the homeworks, otherwise you won't be able to do the problems on the exam. Questions? I can't hear what you're saying. Am I still, oh, so